We're going to start discussing now the human alterations of the carbon cycle. So in our previous discussion, we, we learned that the majority of the carbon is stored in the oceans. But there are some other carbon storage in the atmosphere and in the biosphere, right? And these are the main processes, the main natural processes, and these transport enormous amounts of carbon. And this amount is so big that it may not be compared to the ones that are due to human influences, but there are enough to have to make a significant change on the climate, as we have seen before. So the largest human-driven flux in the carbon cycle is the emission of CO2 from the burning of fossil fuels, and the second one is a perturbation of the land use or the terrestrial ecosystems. But there are some other influences that we're going to discuss that include the cement production. So to start discussing these human influences to the carbon flux, we're going to look at this figure that is the balance from 1990s that includes the input of fossil fuel combustion and land use changes to the carbon that is in the atmosphere. And then we also consider the land uptake and the uptake from the oceans of carbon. So what is important in this figure is that you can see that the total input is bigger than the output. So this difference can help us to estimate the total amount of carbon that is being added to the atmosphere per year. And this is called the airborne fraction, and is estimated from the ratio between the amount that is being remaining in the atmosphere and the amount of that is being added to the atmosphere from anthropogenic additions. When this balance was done from the data of 1990s, this airborne fraction was 38%. Nowadays, the airborne fraction has been estimated to be 45%. Roughly speaking, then, it means that almost less than half of the carbon that we emit to the atmosphere remains there. So fossil fuel and cement are the main inputs of carbon to the atmosphere. And let's analyze then this industrial process of cement production and other processes that also emit CO2 to the atmosphere. So the production of cement from limestone, but also from of steel and aluminum, is from the calcination of limestone to create lime. And this one is the one that produces a lot of CO2 as a result. There are other industrial processes that also emit significant amounts of CO2, and these ones include also the production of soda ash and the use of soda ash and the manufacture of carbon dioxide and also the production of aluminum. But cement accounts for 5% of all anthropogenic carbon emissions. So this is really big. And if we sum the cement, not only the cement production, but the amount of CO2 that is required from the energy that is being required to produce the cement, this number becomes really big. So it comes to a total of 925 kilograms of CO2 per ton of cement. So from these numbers, we can already see where is the problem, right? And one of the problems is construction or human growth and development. But the other one that we can analyze more in detail is the fossil fuels. And the fossil fuels story for carbon emissions, it's very important because it's the one that we can actually tackle to reduce the amount of CO2 that we're pumping into the atmosphere and that is disrupting the carbon balance. Here I'm showing you something that is not new to you, the carbon dioxide emissions from fossil fuels for each country, showing the main ones. And you know that the main emitter is China, followed by United States, and then all the European Union are grouped together, then India, Russia, Japan, etc. But this is very interesting, and this is where the discussion starts. Let's look at the CO2 emissions per capita. And here we see that Australia is the second largest emitter per capita. So it means also that there are two ways to tackle carbon emissions, and one is our lifestyle and how we consume energy, and the other one is where is the energy taken from. And for this, we're going to discuss a very important concept that is called carbon intensity. Carbon intensity is the amount of carbon released per unit of energy delivered. And this one varies depending on the type of source of fossil fuel. Some fuels have high carbon intensity, such as coal, and also some conversion systems release no direct carbon at all. We can also, from this, we can talk about wind turbines or nuclear power. We can also have a balance of carbon if we consider, in the case of biomass fuels, that we can grow new plants that will uptake this carbon, and then we can also reduce the amount of CO2 that is being emitted to the atmosphere. And to tell you also, it's important to remember that no energy system is likely to have zero carbon emissions. So here on the right figure, what I'm showing you is this value, the carbon intensity values for coal and for diesel, gasoline, propane, and then at the bottom is natural gas from the fossil fuels. And we're gonna analyze how these values are being calculated. The carbon intensity is proportional to the energy released during combustion of carbon-based fuels. And this one is dependent on the oxygen they consume. So here, what we are going to need is the stoichiometric equation to know per mole how much CO2 is being released per mole of the fossil fuel here. And here we have coal, oil, and natural gas as examples. Then we're gonna need the low heating value or the high heating value. If we use the high heating value, this high heating value will represent also the energy of condensation of the water vapor form. If we use the low heating value, we'll not consider this latent heat, okay? Because this one actually, in fact, is not available for energy. So when we have these two values, these numbers, we can estimate the carbon intensities of the fuels. And here we have a table that shows some of the values, the estimated values. So what can we get from these values? Something is very evident. When we use natural gas, the carbon intensity is only 15.3 grams of carbon per megajoule, as compared to the 25.8 grams of carbon per megajoule of coal. So this means that switching from coal to natural gas will reduce carbon emissions by about 41% while delivering the same amount of energy. So there is no question about what can we do in order to reduce carbon emissions. But total carbon CO2 emissions not only depends on the carbon intensity of the fuel that we use, it also depends on the population and also on the amount that we emit per capita that is related to our lifestyle, and it is connected actually to the income and to the technology, right? While the technology also covers the carbon intensity and the energy intensity, because it also includes the efficiency and how we use this energy. So then, if we need all these components, we come up with something that we discussed before that is called the IPAT identity. But in the case of the estimation of total CO2 emissions, we're going to talk about Kayak identity. Kayak identity is an equation widely recognized to determine and to also to help to predict future concentrations of carbon dioxide in the atmosphere. And this one uses population, per capita gross domestic product, primary energy, and carbon intensity to determine the carbon emission rate, which is the gigatons of carbon per year. So with the Kayak identity, we can estimate the current or the future carbon emissions depending on different scenarios or different measurements that can be taken. Here we have a way to, an example on how the Kayak identity is being used to estimate, it was used to estimate the carbon emissions for the year of 2010. So when we go to our World in Data website, we can have values of the current population or the past population numbers, the gross per capita per year, and all the values that we need for the Kayak identity. So an advantage of using this identity is that we can separate all these values, and we can see where we need to make changes in order to reduce carbon emissions. So here we can see the CO2 emissions per capita versus the GDP per capita. And we can clearly see that there has to be deeper changes in order to reduce the amount of carbon. And despite that this identity is very useful, it has some limitations. And some of the limitations is that it uses primary energy per GDP as a measure of energy efficiency. However, efficiency can be decreased or increased with modifications in supply. For instance, more efficient electric power plants, and on demand, for instance, by making light bulbs more efficient. So one way to address the two different efficiency improvements is to introduce another factor. But this is not the only one, I must say. There has been several modifications to the Kayak identity in order to accurately assess for other influences on carbon emissions. But this one, for instance, this factor is called final energy, and is the energy purchased by consumers. So this is interesting because it also includes the social aspect, which is the decision, right? And another extension is based on prospects for carbon capture and storage in the future. And you know that this is very important all over the world, and is something that is being claimed as a way of not making some changes in the type of fossil fuel that we're using or the lifestyle that we're using, because now we're claiming that we can storage carbon. And there are several technologies that are being tested in order to capture CO2 from the atmosphere.